Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1411, also known as General Chemistry 1. So we're going to be covering a couple different concepts today. We're going to be covering Lewis structures, the octet rule, shapes of structures, and sigma pi bonds. The first thing we're covering is Lewis dot structures. To draw Lewis structures for any main group element, you have to note a group number. So that is that number that is on the top. So group 1A, 2A, so on and so forth until you get to 8A. And that is going to give you the number of valence electrons. So if I have a group 1A element, such as hydrogen, I'm going to have one valence electron or one dot around its symbol. If I have a group 6A, I'm going to have 6 valence electrons, and it just kind of corresponds with whatever group the element you're looking at goes to. So you're going to place one dot at a time on each of the 4 sides of the element symbol. Keep adding dots until you have paired them and all of the valence electrons are used. So here is an example of kind of what I'm talking about. So oxygen is a group 6A element. So it should have 6 valence electrons surrounding its symbol. So what you'll do is you start, pretty much you can start from any side you want. I normally start from the top, but it's really your choice. And you just add 1 electron per side until you reach 6. So you say 1, 2, 3, 4, 5, 6. I hit all 6, so I stop there. Fluorine would have 7 because it's group 7A, and then nitrogen would have 5 because it's a group 5A element. So now let's go ahead and work on a couple of our own. So we're going to do the Lewis dot structure for sulfur, argon, and bromine. All right, so let's start with sulfur. Sulfur has the symbol of S. So sulfur, the first thing I'm going to do is going to write my symbol. Sulfur is a group 6A element, so I should have 6 dots surrounding it. So I'll do 1, 2, 3, 4, 5, 6. Once I have all 6, I'm done, and this is my Lewis dot structure for sulfur. I now have argon. So argon has AR as its symbol. So I just draw my symbol right here, and argon is a group 8A element. So I have 8 valence electrons surrounding it. So 1, 2, 3, 4, 5, 6, 7, 8. It has all 8, so this would be the Lewis dot structure for argon. And then finally, I have bromine. So bromine is going to have the symbol of Br. Bromine is a group 7A element, so 7 valence electrons surrounding it. So 1, 2, 3, 4, 5, 6, 7. So this would be the Lewis structure for bromine. And that completes our example 1. Now we're going to move on to something called the octet rule. The octet rule is a chemical rule of thumb that reflects observations that atoms of the main group elements, so everything with the A on its group, tends to combine in such a way that each atom has 8 electrons in its valence shell, giving it the same electron configuration as a noble gas, with exceptions of hydrogen and helium. So hydrogen and helium are the only 2 that do not want 8, they only want 2, which is why with hydrogen and helium, we're only going to see it be able to form a single bond with another element. Everything else prefers to have 8 surrounding it. So everything else we need, when we count how many are around it, it will have 8. So this is a visual example of what I'm talking about. We have oxygen and we have hydrogen that are coming together to form water. So oxygen is a group 6A element, so we notice that it will have 6 valence electrons surrounding it. Hydrogen is a group 1A, so it only has 1 valence electron in its shell. When they come together, you see right here, these two dots form a bond between the oxygen and the hydrogen. So the hydrogen has 2 on each of these hydrogens. They have 2, which is what hydrogen wanted. And then oxygen now has 8. So we count 2, 4, 6, 8. And that's what we're referring to when we say the octet rule. So now we're going to cover Lewis structures for compounds. The least electronegative element is going to be your central element. So that's why oxygen was our central element in water. And that's because we have to have the exception of hydrogen. So if you have a compound such as CH4, even though hydrogen might be the more electronegative, it is the exception. So carbon in a CH4 compound would be our central element. At least 1 electron from each element will be used to form a bond. So to have a compound, you have to have things bonded together. So the 1 valence electron from the hydrogen will pair up with 1 valence electron from oxygen to form a bond between them. And then we can determine how many bonds a compound will have using the following equation, which is shared pairs equals 1/2 times the electrons required, which is going to be how many they prefer to have. So all elements with the exception of hydrogen and helium will have 8, and for helium and hydrogen it will be 2, minus the valence electrons available. So that's going to be how many it actually has. So hydrogen would have 1, carbon would have 4 because it's a group 4A element. And we'll be able to go through this equation in our next example. And then if a specific question asks for you to draw the Lewis dot structure, you have to show all the valence electrons. So in place of drawing a Lewis structure, so a Lewis dot structure, you have to have the dots. Lewis structure, you can show a bond, which can be shown with a single line is a bond. But if you're doing the Lewis dot structure, you're going to have 2 dots that represent a bond. So that's kind of what the difference can be. So let's go through an example of the equation that we showed before to show how many shared pairs or how many bonds we will have. So we have Sp equals 1/2 Er minus Ve. So this is how we calculate Er. So we have the compound of C2H2. So carbon wants to have 8 valence electrons, and we have 2 of them. So we say 2 times 8 will take into account the carbon. Hydrogen only wants 2 valence electrons, and we have 2 of them. So we say 2 times 2 because that's all it wants. And when we add that together, we will get 20. Then for the valence electrons or the Ve, we have 2 carbon elements, and each carbon is in a group 4A. So we say 2 times 4 plus 2 hydrogen times 1 because it's a group 1A, and we get 10 electrons. We plug both of those values into our equation, and we say 1/2 20 minus 10. When you multiply that together, you'll get 5 as your answer, which means I should have 5 shared pairs or 5 bonds. And this is what the structure looks like. So we can see that we have 5 bonds. We have 1, 2, 3 between the carbons, 4 right here, 5 right there, and we reached all 5 pairs. We also notice that they correspond with the octet rule. So 2, 4, 6, 8 for this carbon, 2, 4, 6, 8 for this carbon, and then the hydrogens will just have 2 because that's how they are happy. So let's go through and do the calculation on our own. So we're going to calculate how many bonds O2 will produce. So we have the compound of O2, and our equation is shared pairs, which is going to be shown with an SP. So shared pairs equals 1/2 our electrons required, which is going to be designated with an ER, minus the valence electrons available, which is VE. And this is how you're going to kind of see the formula set up. So we can start by calculating our ER. So we have 2 oxygen elements. So we say 2 times. The oxygen wants to meet that octet rule, so it wants 8 valence electrons. So you say times 8. So 2 times 8 will give me 16. And then for valence electrons that I have 2. So I say 2 times. The oxygen is in the group 6A. It's a group 6A element. So you're going to say 6 here. So 2 times 6 will give me 12. And now I can plug these 2 into my equation. So I say SP equals 1/2 times 16 minus 12. So 16 minus 12 will give me 4. So it says equal 1/2 times 4. So my SP is 2. I have 2 bonds between my oxygen. So it's not required, but I'm going to go ahead and show you what it looks like. So I have oxygen with 2 bonds, but each of these oxygens wants 6. So they have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It now has 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. So each oxygen meets that octet rule as well. So I know that my structure is good. So now it wants us to draw the Lewis structure for the following compounds. So we're going to do H2O, which is water, CH4, and NH3. So let's go ahead and go to our boogie board. So our first one is H2O. So we have to figure out what our central element is. It's the least electronegative element with exceptions of hydrogen. Well, I only have oxygen and hydrogen, which means oxygen, by default, is my central element. I know that I'm going to have hydrogen, so I'm just going to go ahead and draw them here. I'm not going to draw anything else until I figure out how many bonds I want to do. So let's figure out how many bonds by just practicing that equation that we did before. So we have SP equals 1/2 ER minus VE, or ER, equals, we have 2 hydrogen, so we say 2 times, it only wants 2 valence electrons, so 2 times 2, plus we have 1 oxygen, times it wants 8 valence electrons, so we have to put 8 here. So we get a total of 12. And now we can calculate our VE. So our VE, we have 2 hydrogen. It's in a group 1A, so we say 1, so 2 times 1, plus our oxygen, we have 1 of them, times, it's a group 6A, so we say 6. When we add these together, we get 8 as our VE. And so now we can plug 12 and 8 into our equation. So we have SP equals 1/2 12 minus 8. And so our SP will be 2. So I should have 2 bonds in my water molecule. So 1 bond here, 1 bond there. Hydrogen has completed its little octet because it only actually needs 2. However, I have to finish my oxygen. So oxygen has 6 valence electrons. Right now we only have 2. So 2, 3, 4, 5, 6. So now I can check to see, do I have the octet rule down? 2, 4, 6, 8. I meet the octet rule for my oxygen, so I am good to go on water. Now we can do CH4. Because I only have carbon and hydrogen, carbon by default has to be my central element. So I have carbon, hydrogen, 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 and hydrogen because I have 4 of them. But we're not going to put anything until I know for sure how many bonds I want. So we can plug it in. We have sp equals 1/2 Er minus VE. So I can calculate my ER. It's going to be 1 carbon. It wants 8 valence electrons. And we have 4 hydrogens that want 2 valence electrons. So my ER will be 16. My VE, I have 1 carbon. It's in a group 4A. And then I have 4 hydrogen that is in a group 1A. So when I add these up, I get a VE of 8. And now I can plug it into the equation. So SP equals 1/2, 16 minus 8. So my SP will be 4. So 1, 2, 3, 4. Hydrogen each have 2, so it meets its rule. Carbon has 2, 4, 6, 8, so it also meets the octet rule. So I'm done with this formula, or with this structure. And now we can move to NH3. So once again, I only have nitrogens and hydrogens. So nitrogen will be my central element. And I can put a hydrogen here, here, and here, because we know we have 3 of them. And we start our equation. So 1/2 ER minus VE. ER, we have 1 nitrogen. It wants 8 valence electrons plus 3 hydrogens that want 2 valence electrons. Let me move that in real quick so it doesn't cut it off. There we go. And so our ER is going to be 14. And now we can calculate our VE. So we have 1 nitrogen. It's in a group 5A, so it has 5 valence electrons, plus we have 3 hydrogens that is in a group 1A, and so our VE equals 8. And then now we can plug our ER and VE into our equation. So SP equals 1/2 times 14 minus 8. So my SP will be 3. So I have 3 bonds. 1, 2, 3. My hydrogens all meet their little rule. Nitrogen 2, 4, 6. So we realize that nitrogen has not met its octet rule. So I go back and I think nitrogen is in a group 5A. So it needs 5 valence electrons surrounding it. We have 1, 2, 3 right now, so we need to say 4, 5. So now 2, 4, 6, 8, it meets the octet rule, and this would be its structure. So let's go back over here. Our next topic is going to be the VSEPR theory. And VSEPR stands for valence shell electron pair repulsion theory. So it's kind of a long phrase, but most of the time you'll see it as Vesper. And it states that the shape of the molecule is determined by repulsions between all the electrons present in the valence shell. Electron pairs in the valence shell of the central atom repel each other and align themselves to minimize this repulsion. Lone pair electrons take up more space around the central atom than a bonded pair. Lone pair attracted to one nucleus, but one bond pair is shared by two nuclei. And the minimum repulsions to the state minimum energy and maximum stability of the molecule. And this will make a little bit more sense when you actually see a molecule. So this is kind of what it's talking about. So you see that the bonds themselves take up less room than these lone pairs. So these two dots are just the little valence electrons that we placed on our oxygen. But you have to think of having a little balloon around them. So each of the lone pairs take up more space. And so it's going to push your hydrogens down, and the water molecule will form a bent molecule. And so the shapes are what we're actually talking about with the Vesper theory. And so this chart right here kind of puts all of it together. So it's broken up into 5 different categories. So I have the number of electron groups. So electron groups are going to be single bonds, double bonds, triple bonds, and lone pairs. So you count how many are around that central element, and that will fit into one of these categories. You have your general formula, which is AX, and then there's sometimes an E. Your A is going to represent your central atom, so whatever your central element is. Every formula will have an A because you have to have a central element. Your X, so the X is here, so it says X2. That means I have 2 atoms surrounding that central atom. So I have 2 things attached to it, such as like oxygen, water. I have oxygen with 2 hydrogens attached. And then your E is going to represent lone pairs of electrons that are attached to the central element. So you're only counting the ones that are attached to the central element. And based off of which category it fits into, it's going to tell you the molecular geometry. And that is just pretty much the name that we show, that we say it is to represent the shape it's going to take form. And then with each molecular geometry, we're going to have bond angles because things are going to be like moved in certain directions, and so between those bonds, there's going to be a specific angle that corresponds with the molecular geometry. And then my 5th category is just an example of each. So if you wanted to see or look up each of these compounds and their structure, you could see what the molecular geometry looks like. But I'm going to show you one as well. So this kind of shows you what each of them look like. So a linear, well, linear means line. So we have it in a flat linear position. Trigonal planar, you're going to have, it kind of looks like a sideways Y. Bent, some of them will have the lone pair right up here, but we have another pair bent that has 2 sets of lone pairs. So you'll have it kind of looking like a, like the elements themselves will be bent, but you'll have your lone pairs up top, either pointing straight up or to the side, kind of like these ones right here. We have tetrahedral, which is going to be, there's 4 things coming out. So these 2 are going to be pointing to the sides, and then you'll notice the little dotted line and the solid line. Those actually represent something pointing inwards and outwards. So it's going to be pointing either towards you or away from you. We have trigonal pyramidal. So it's pretty similar to our tetrahedral just slightly different because instead of having 4 electrons attached or elements attached to our central element, we have 3 and a lone pair. And it kind of just keeps going on and on until you hit whatever molecular shape you're looking for. So here are a couple steps on determining the molecular shape. These are the things you should think about when you're working with a VSEPR problem. So the first thing you should ask yourself is how many things are there around the central element or atom? So look at how many atoms or elements there are that are attached to that central atom. 2, are there any lone pairs on the central atom? So you have to look at it and say, do I have any lone pairs? Because those lone pairs will change the molecular geometry. What shape do the previous answers correspond to? So you'll figure out what general formula corresponds with your answer to question 1 and 2. And that will tell you the molecular geometry. And then number 4, what bond angle corresponds with the previous shape? So after you determine 3, you can determine what the bond angle is. And this chart right here, it won't be provided for you. At least with most professors, it won't be. So this is something you'll have to try to memorize, or you can put it in your own way. This is just how I present it. But knowing this will help you answer these questions. So let's go ahead and go through a couple examples of our own. So let's go to our boogie board. Our first element is CO2. So we have CO2. Our central element is going to be carbon. So we have carbon. We know we have 2 oxygen. And we can either use the equation that we used previously, or we can kind of just go based off of what we know. So we know that oxygen needs 6 valence electrons, carbon needs 4. So if we went through that equation that we had done previously, so the SP equals 1/2 times ER minus VE, we realize it needs 4 bonds. There's only 3 elements, which tells us that we have 2 double bonds. So carbon now has 1, 2, 3, 4 valence electrons of its own, and it shares 2, 4, 6, 8. So it meets the octet rule. And then we have oxygen, which needs 6. So 1, 2, 3, 4, 5, 6. Same thing over here. 1, 2, 3, 4, 5, 6. 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. It meets that octet rule. So this is my structure. And you need to know that structure to be able to determine the answers that we had to ask ourselves. So are there elements surrounding it? Yes. So the first thing we have is our central element. So we have an A. X tells us how many other elements there are attaching to it. So we have 1, 2. We have 2 elements attached to it. So we have an X2. And we have to look, do we have any lone pairs? No. This ends the general formula. Think about what corresponds with it. It's going to be a linear equation, and it's going to have 180 degrees. So linear answers our first part, 180 answers our second part. And it's really just memorizing that chart and knowing what corresponds with each other. So now we have SO2. So our central element is going to be sulfur, which means we have oxygen that are attaching to it. When we go through our equation, we'll find out it needs 3 bonds. So it doesn't really matter which one we put it to, so we can just do 1, 2, 3, and that has 3 bonds. And then we will go ahead and put our lone pairs with where they go. So this is the structure I'm looking at. So now I need to determine my general formula. So I first write my central element. So I have A. I have two elements that are attached to it. So I have x2. And then I also have a set of lone pairs. So I have to write E. So I have an AX2E as my general formula for SO2. So AX2E is bent, and it's going to have 120 degrees. So these are my answers, and so it won't actually look like this. It would be S, oxygen, oxygen, with my lone pairs up here. So this is what this structure would look like. And then now we move to XeO3. Our central element is Xe. So we say Xe. We know we're going to have 3 oxygen. And Xe needs 8. So after you can kind of do the guess and check game if you want to see it like, okay, if I had 1 bond each, what would it look like? But after a while, you realize that it has to go with this formation right here. Yes, Xe is an element that is different. It doesn't need to meet that octet rule. It's going to have way more than that octet. But we also have to fill in our valence electrons for our oxygens. And this is what the structure is going to look like. So now that I know my structure, I can say my central element, so A, I have 3 other elements surrounding it, so I have an X3, and I have a set of lone pairs, so I say E. So I have AX3E as my element, or my general formula. This corresponds with a trigonal pyramidal. So and it's going to have 109 for the degrees. And so really knowing that chart or coming up with a chart of your own that helps you better understand the material and how they relate to each other is really going to be important for this type of problem. And finally, our last topic is sigma and pi bonds. Sigma bonds are bonds formed by end overlap of atomic orbitals. So that's what this picture right up here represents. So this is 2s orbitals. It's just overlapping right here where they connect. And then my 2p orbitals, they have to connect through pretty much, I call this the head. So they connect right here, they're overlapping, and that would be considered a sigma bond. A pi bond are bonds formed from side-to-side overlap of p orbitals only. So we have our p orbitals right here, and they're side-to-side, so that you see the difference. This one's head, this is side-to-side, and these are going to be pi bonds. But a majority of the time, you won't see it set up like this. You'll see it with this information right here. So they'll ask you kind of determine how many sigma and pi bonds this molecule has. And so you'd have a structure, and you, based off looking at the structure, you determine how many sigma and pi bonds you actually have. So if you have a single bond corresponds with 1 sigma bond. A double bond is 1 sigma and 1 pi. And then a triple bond is 1 sigma and 2 pi. And so you simply identify what each of the bonds represent, add them together, and that's how many sigma and pi you have for that compound. So let's go through an example. We have this structure right here, and we want to know how many sigma and pi bonds we have. So let's go ahead and go to our boogie board. So we have H, C, C, H. So let's go ahead and start to identify what each of them gives us. This single bond right here gives me 1 sigma. Same thing here. I also get 1 sigma. I have a triple bond, so this triple bond corresponds with 1 sigma and 2 pi. And that's all the bonds I have. Sometimes they can give you a long structure, and all you have to do is sit there and add them up. So I have 1, 2, 3. I have 3 sigma and 2 pi bonds in this compound. And so it's just as simple as that. So even if you have a long, like I said, a long chain of elements, just simply sit there and count how many single bonds you have. You know, each single bond corresponds with a sigma. Count how many double bonds. That gives you 1 sigma, 1 pi. Count how many triple bonds. That gives you 1 sigma, 2 pi. Once you finish, add all that up, and that would be the number for your compound. And that wraps up everything we have today. So let's do a brief overview of everything we covered. We covered the Lewis structures, which we need to know that the valence electron is equal to the group number. So that's going to be the main thing you need to know for drawing a Lewis dot structure. Also, that branches off the Lewis structures is the octet rule. And it states that elements want to have 8 valence electrons, with exceptions of hydrogen and helium, which only want 2. We then covered the molecular shapes, which we covered the Vesper theory. So that is going to tell you the shape that your compound will take place based off of how many electron groups it has, how many, if it does have any lone pairs. So knowing that chart that I showed you before, or like I said, making your own, will really help you understand the material, and it really just takes a lot of practice. And then the final thing we covered was sigma and pi bonds, where we learned that a single bond corresponds with 1 sigma, double is 1 sigma, 1 pi, and triple is going to be 1 sigma and 2 pi. And that's all we have for today. I hope this video was helpful. Thank you for watching, and have a great day.